Hey everybody. Today I want to talk about electric cars. Now, I want to do this at the point of view of a car enthusiast that I am. And, you know, I'm into my old Camaro, my old Mustang. I love the classic cars. But today I wanted to bring some thoughts for the future. This won't be like an engineering course in electric cars, but kind of a high level of, gee, if you're a car enthusiast and you love to work on your old classics, what are we going to be dealing with when electric cars come down the road? I mean, they're around us already, but they're probably, you're going to see more and more of them. I'll say, for full disclosure, I don't own an electric car. All mine are gas powered, and I'm not ready to make that transition myself. Yet they're a good fit. You know, electric cars are a good fit for some people. So as a car enthusiast, I thought it might be good to talk about, you know, what electric cars are all about, and you know, what's coming down the road toward us. I'll just say that, you know, throughout my life, working on cars and things, and working in automobile engineering after I was a little older. I mean, I was helping my dad tune up cars when I was 7 or 8 years old, so I've been at this a while. And, you know, my thought has always been, I love performance cars, but we've always been working toward making things more efficient. You know, we really should be good stewards of the environment and good stewards of resources. And so, you know, I like cars that make a lot of power, but as we go on, you know, we should work to clean the air, we should work to use less fuel and so forth. Well, these electric vehicles get to be really the, I'll say, that's probably as far as you can go. And some would say, you know, are they far enough? Well, so enough with that. You know, electric cars, what should a car enthusiast think about electric cars? Recognize today that, you know, hybrid and electric cars are in the news, and actually hybrid cars seem to be reduced in significance because the big push seems to be to go to full electric. You know, electrification of vehicles starts with very mild hybrids. I used to work on some where, you know, our motors were 15 or 20 kilowatts, 15 horsepower maybe. You can run from that light end, you know, all the way up to full electrification. I'm going to use the word BEV quite a bit, or it's actually an acronym, but it stands for Battery Electric Vehicle. So when you say electric car, I'm talking about BEVs. There's a big push in the world right now to go to BEVs, and we're seeing it around the world. And with this idea that we need to get to net zero and produce no carbon. You know, if you really wanted to get partial carbon, if you want to make improvements, hybrids are a great way to get there and reduce consumption and have a great performing car. And it's kind of the combination of electric and conventional powertrains. The criticism of those is that you need both systems, but you can run it with a lot smaller battery. And, you know, there are probably some really good questions about where's this net zero coming from, and is it even practical? Can we even do it? Because, you know, net zero, I don't want to dive into that today, but if you're going to force the entire transportation network and everybody's house to go all electric, no natural gas, no gasoline, that means you need a lot of electrical generating capacity. And they want to do it all from windmills and solar. And just from my experience, that's a really tough act. You know, it's really a tough nut to crack, so to speak. Anyway, it's a difficult challenge, but as governments are putting in legislation, we're going to be dealing with it here more and more coming soon. So today, rather than talking about hybrids, I really do want to talk about BEVs and what's in a BEV, and, you know, would you want one as a car enthusiast? You want one. And if you had to have one, what would you do? So what are the pros and cons? And to understand that, you need a little bit about what's the hardware in an electric car. What are you looking at? And again, I'm going to try to give you a relatively simple view. And then, hey, from the standpoint of performance, as a car enthusiast, what could you do? What can you do, right? So I'm going to take just a minute and give you just a little of my background so you understand that I'm not, I'll say, making this up out of thin air. I've worked in this now for quite a while. I've got, I've been in the automotive engineering business since I was a student in college for, literally 40 plus years. And the last 15 years were in hybrid and electric. And I've worked on, engines, transmissions, axles, shifters, just about everything that goes into a propulsion system or a powertrain. And with a great concentration on how you integrate all those pieces and make them work as a system. I always kind of said, no offense to people who design door hinges, we need them. But I never wanted to be a door hinge engineer. I always wanted to be bigger. I was more, let's take the whole system. That was where, say I got excited about things. And I had this great opportunity in around 2003 to get in when General Motors was really starting to they saw hybrids as the thing that was coming. And we were working very hard, recognizing fuel efficiency and advanced technology to come in and start building hybrids, which then morphed into, as time went on, into electric vehicles. I had a number of different roles. Most often I was leading technical teams that were putting propulsion systems together and marrying engines and transmissions and electric motors. Later on I spent time with full electric, with BEVs, and I've had roles in all of those different vehicles over time. This will be a little GM centric, but we were toward the front end, right? At least in the United States. I know a lot of people built electric cars, one-off or two or three in modern times. But GM, the EV1 was the first electric vehicle that was pretty much mass-produced in the, modern times. It was around, late 1990s that was out, and in through the early 2000s. It was leased rather than sold to the public. There were about, if I remember correctly, they built 1,000 of them. There were lots of reasons why the company wanted to lease them and not put them out in the field and sell them. And some of those things, they revolve around how do you do service parts and, build a car, that goes out in the field for 10 or 15 or 20 years and support that. And in a car that was really leading edge. So you had a two-seat with lead-acid batteries. It performed very nicely. It would run down the freeway at highway speeds just wonderfully. When I got into hybrids, they weren't actively leasing them anymore, but we had them in the fleet, and I had an opportunity to take them home and drive them. And at that point, they had already had an upgrade to nickel metal hydride batteries, which increased the range. And even there, my first experience with electric cars was a range anxiety kind of a thing. I lived 35 miles from the facility. Much of it was interstate type driving. I took a car, I drove it home, I drove it around the neighborhood, I took my kids out on demo rides, I drove the car and took them for rides, and a few miles here and there. And in the morning, it was a fall morning, it wasn't cold, but I had to defog the windows and things because it was that time of year. And by the time I got back, it should have been about an 80-mile round trip. I had 120 miles on the meter when I started, and by golly, I was down to 10 miles and starting to sweat. So the people who talk about range anxiety, it's a real thing. If you've got a car, this one had a relatively short range. And I didn't have charging capability. They offered me a charger, but it was a huge thing that it just wasn't practical to take home. So I was just, I'm going to be careful, right? And I was. I made it back. I still had 10 miles of electricity. The thing is that, when I get in my gas-powered car, when I get below about 50 miles, I'm heading for a gas station. Actually, when I get below 100, I'm starting to go to a gas station. It's a different thing that you have to learn. Second electric car was, and I didn't work a lot on this one, this was my colleagues down the hall, was the Chevrolet Volt. And a lot of people went, oh, that's a hybrid, that's a hybrid. Well, we called it an EREV, an extended range electric vehicle, because essentially it ran like an electric car until you ran out of battery. And then the gas engine kicked in and you could drive as long as you had gasoline, you could keep on going. And I drove those and took them home, and I experienced that, and it was really nice, because if you plugged it in, you went where you were going, and you happened to get too many miles and the battery got low, the engine would kick in, and with hardly a disturbance, I mean, it would just transition, the engine would fire up and take over, and you'd keep on going. The beauty of that was that it was a relatively small battery. You didn't have to try to protect for a 100-mile range. And I don't remember all the details, but I remember at the time when we did that some studies were done, and those studies were done mostly around looking at the California market. But the overwhelming majority of people from a commuting standpoint could survive on a 35-mile battery by either they were less than 35 miles round trip, or if they were further, they could plug the car in at work at the other end and have enough to drive home. And so it made a 35 to 40 mile range a very practical electric car. But you still needed the full powertrain. And the distinction is that there are many others out there that are what's called plug-in hybrids. And while this was a form of a plug-in hybrid, the difference was that you could, when you would go wide open throttle on a Volt, you would get maximum performance, and the engine would not kick in unless the battery was down. Many of the plug-in hybrids, if you drive around town at moderate throttle, stay electric, but if you really went to wide open throttle, you're going to get the engine kicking in even if the battery's still got power with it. Depends on the car. I can't speak for all of them, but that tended to be, in that time when the Volt was developed, that was the competitive space. So today, I mean, we just have so many different models. Tesla came out around, I think it was 2008 with their first model. We followed with some models, I don't remember exactly, but it was around 2010, 11, 12, we began getting BEVs out there. It became to the point where we started trying to add electric vehicles along with our hybrids. And now, if you look at what's out there, GM has said, hey, we're going to try to go all electric, complete. Many of the companies around the world are working in that. And so you're going to find a wide range of models. And I can't speak for all of those. I'm going to give you some generalities of what these tend to look like. Recognize that you'd have to go look at the specs for each individual one and see what they are, see what you have. So advantages. There are advantages to electric cars, and one is they don't produce any CO2 if you can get fully renewable solar or wind energy. And right now that's actually a challenge. And many of our BEVs are being powered by coal-fired power plants. From a full life cycle standpoint, you're not always zero carbon, I'll just put it that way. But one of the coolest things about electric cars is just the performance, especially performance off the stop. The electric motors just have so much torque, so much launch torque, that they accelerate smoothly, they're really quick. There are ways, you can put 2 motors or 3 motors in an electric in a BEV far easier than you could ever think about putting 2 engines in a gas car, right? To get all-wheel drive, you can put a motor on each end of the car, on each axle, and as long as you have enough battery to run both of them, yeah, you need more hardware, but it's a lot easier than you might think in some cases. And it's like we talked about the new Corvette. That's a hybrid, right? it's got a gas engine powering the back wheels and an electric motor powering the front wheels to get an all-wheel drive without going through all the hardware that you would need to transfer power from the rear of the car to the front. And you get extra power because you got the battery. So things to think about. Electric cars, most of the time, are pretty quiet. They're really quiet. Now if you're inside, there are certainly some whines and things that you can get out of gears and power electronics and motors and so forth. And the engineers in the cars I worked on, we worked really, really hard to get noises down so things were quiet. Your mileage may vary. If you look at different models, that's just something to check. There are some inherent noises that you get out of motors and associated equipment. But these cars generally are so quiet that in most places, from a regulatory standpoint, we actually had to put in noisemakers, pedestrian warning devices. Now, this is not like a horn, but many of the cars, because they're so quiet, if you were, they could sneak up on a pedestrian, you wouldn't hear them coming, especially if there was other traffic around. And so regulations came up that actually put, they would put devices in that would generate a tone of some sort, trying to be unobtrusive, but something that would give it enough noise, background noise, that someone would hear it coming. Regular maintenance. There aren't any oil changes. You don't have to change the air filter, the PCV valve, the spark plugs. I mean, on a gas car these days, you go 100,000 miles on spark plugs, but recognize that routine maintenance is much less. You still may have maintenance on brakes and suspension and so forth, but it's much less, and there are fewer things to repair. Charging. A lot of people, they go to home charging. They get supply equipment installed in their garage or at their house. And most common in the United States is 220 volt 50 amp. Sometimes you can run 30 amp service, which would be like what an electric dryer normally uses. 50 amp is about what a 40 or 50 is usually what a electric range will draw. So it's that type of a circuit. And that's usually pretty adequate. I haven't seen bigger services, but I'm sure there would be some. And there are places where you could use three-phase. But generally in the U.S., unless you're in an industrial site, you use the 220 50 amp as your base, and it's pretty effective. There are people working on things like wireless charging, where you'd have a mat on your garage floor and you'd bring the car in and park over the mat, and it would charge the battery automatically for you. As you look at what happens out in the world, there are a lot of people worried about battery life. And lithium batteries, properly cared for, will last a very, very long time. In my hybrid world, when I was doing mild hybrids, we had batteries that were smaller, and we used them pretty hard. And we would go through a charge and discharge cycle. We could charge them and discharge them maybe in a mile or two. And we would deplete them pretty fast, and you could fill them back up again. If you were in the mountains or in the hills, you'd fill it up going downhill, and you'd deplete it going up the next one. And we could easily do 200,000 miles worth of life on those batteries. It was not a problem. We did test work where you could run a long time. When you get into BEVs, you don't have as many cycles, and the battery's much bigger. So when I say with proper care, some of that's on your manufacturer. The manufacturer is going to limit your battery usage to try to protect the battery and keep it in range. But some of these, you can fast charge a battery sometimes and get it really, charge them really quickly. But sometimes if you do that too often, it will take some life out of your battery. Now on the challenge side, range anxiety, depending on the car. There's a great debate in the industry right now about how big should the battery be, because the bigger it is, the heavier it is, the more expensive it is. So there are thoughts that for people who are doing city cars, maybe you want a smaller battery. Just recognize that those of us running gasoline cars, right? The EPA, federal U.S. EPA, has done gasoline fuel mileage ratings since the 1970s, right? They started about 1975 or so. And they've been tinkering with those ratings. The basic tests haven't changed a lot. The basic 2 cycles, they've added cycles, some of which are optional. And that's a really deep hole to get into too. But basically the 2 cycles haven't changed, but the adjustments to the cycles have changed. So typically speaking, you go run your fuel economy test for certification in the laboratory on a dynamometer, and the D rates are in the order of around 20%. And again, it's more complicated than that, but just for the sake of discussion, you know, that the gas cars have D rates because the test is optimistic. The electric cars are kind of, I think, in that same realm right now, where they're trying to get, I would say they're still tinkering with the different factors. And I see reports from the field of people who say, hey, I'm not getting the range that I expected. Well, you know, those tests are all run under controlled conditions at certain temperatures. So when it's hot out, when it's cold out, if you're running at higher speeds, perhaps you're in the 75 speed limit range, or you're running 75 or 80 miles an hour or something. Not advocating running over the speed limit, but recognizing where the traffic is running some places. You know, most of the time that's higher cruise speeds than you'll find in the federal test procedures. So just be aware, look at how they measure the range if you're looking at an electric car, and see where that falls out. Battery storage density, no matter how you look at it, batteries don't store anywhere near the energy of gasoline. You know, gasoline and diesel, you know, BTUs per gallon per cubic foot, take your measurement, is many times what a battery is today. Now, as we go forward and people keep improving chemistries, maybe the day will come when they match, but today they don't. Weight, battery packs are heavy. They're not heavy like lead acid. Don't misunderstand me. I love lithium batteries because they're a fraction of the weight of a lead battery. But when you get to a car with 300 miles of range and you've got battery, even lithium cells across, you know, the whole floor pan, it's a substantial amount of weight. You know, look at the specs if you're looking at a particular model. Charging. On the positive, you can charge at home. On the positive, there are fast chargers out in the world, and you can charge in, like, you know, some of them will go to 80% in 30 minutes, maybe even less. Depends. This is all. It depends. It's how big is your pack, how big is your fast charger, what's your temperature outside. You can charge pretty fast. Now, if the battery pack is cold, if it's below freezing out, you won't be able to pump as much current in as fast. On the other side, I said on my slide here, I said 4 days. Well, if all you have available to you is a 15 amp 110 volt plug in the wall, many of these cars, you know, kind of have a backup plug that you can plug into 110. But if you got a large pack, it will take you a very, very long time. The advantage is to have an upsized charger. Bidirectional charging, this is just an interesting one to throw in there, is that there's a lot of work going on bidirectional charging, which means that if you've got your car plugged in the garage at night and the grid starts having challenges, that the grid might pull power off of your battery to maintain your neighborhood. Don't know how that's going to work out, but it's out there. Just battery issues. Again, if you look outside, and I hear comments from people, I see comments online in different places, and there's a lot of concern around batteries. And you'll see reports of fires. You really have to watch if you're working on one of these cars as a car enthusiast. If you want to do any work on them, that you get the training for high voltage, because shock hazards are very, very significant. And you have to really know, each car, each model has different procedures for how you disable them. Fire risk, as I mentioned, there are some inherent risks in lithium-ion batteries in their failure modes. I will tell you that in my experience, I worked with battery people who were being extremely diligent and working to make those batteries as reliable as they possibly could. That any of those risks would be very, very small, but they're not zero. It's out there. There are tests where they puncture battery cells, they run them hot. There are all kinds of abusive tests that are run to qualify a battery. Temperature limits, they're happiest probably between, depends on the exact chemistry, but they're probably happiest between 50 degrees and 75 degrees Fahrenheit. And then the colder you go or the higher you go, what the software will do is limit the amount of current that you can add to the pack or draw from the pack. And some of you may see this even on your own cell phone, right? If your cell phone gets hot and you're trying to charge it, at least my Samsung, I'll get a message saying that the phone is too warm, and it'll tell me to turn off the display, stop recording video. It'll ask me, it'll give me warning messages if the phone happens to be getting too warm. Power electronics. Power electronics is an interesting, when I say power, that's where inverters and chargers and things, you're running a lot of current at high voltage through these devices, and like everything else, they have the possibility of failing and needing replacement or blowing fuses. There are risks out there. And the same thing I said about learning to service a car. If you don't have the training, don't touch them, because in my experience, we always tried to protect and cover things and to keep people from accidentally getting in and touching high voltage. There's a lot of safety that gets designed in, but I can't talk for every manufacturer that they all go through that same level. If you're going to go poking your head under as a car enthusiast, make sure you know what you're doing. Now, let's talk about power, motors, right? Here's a couple of charts. The one on the right is it's a GM torque curve for a 6-liter V8. And 6-liter, usually we use those in the 1-tons, but pickup trucks like in the Seath, Silver, what do they call them? Usually we use those like in the Silverado HDs. 2500s and 3500s. Anyway, if you look where the red circle is off here to the left, you'll see that the power curve, see the peak torque is around 360, and it tails off, and down here at 1000 RPM, it's going down pretty fast. And at zero, it'll be zero, right? And then the horsepower peaks out here at 4400. And that's a fairly typical torque curve for a normally aspirated gas engine in terms of its shape, right? Now I'm going to go over to the left, and you can see my legend here says excellent low-end torque. Well, this is the torque curve, this blue. So you start off really high, you come out to this corner that they call the base speed. And then, so it's like constant torque below base speed and constant horsepower above base speed. Now, this is a theoretical curve, and there are losses, and sometimes these curves will, sometimes below base speed, things will fall off a little bit. But I had motors that I ran in hybrid vehicles that were very, very close to this. If it's properly designed and calibrated and tuned by the engineers, this is a very practical curve. So, here I had on an engine that was 360. I created this curve, and the calculations for horsepower are just, I arbitrarily said I got a 350 foot-pound motor. And real life, if I was back working, I would take this, we would put that in as a requirement, and then the motor design team would be looking at what different kinds of windings and how much copper and how much steel and what would it take to generate that. But so this is theoretical, but just recognize that if you were trying to do apples and apples between a 6-liter V8 and an electric motor, this is the kind of the base characteristic. And so, down at low speed you'd have maximum torque, and then that torque would fall off as the engine speed or motor speed came up, and the horsepower would come up at low, and then the horsepower would be constant as you go out to high speed. Again, there are spun losses, there are other kinds of factors, but this is really pretty close to how most of them operate. This is enabled a lot by some of the latest technologies in motor drive systems. I've talked to people and I've seen different people consider different ways. What is an electric car? What's in it? What do you think is in an electric car, right? You're a car enthusiast, right? You work on classic cars with engines. What do you think's in an electric car? Many people kind of have I'm going to call it the golf cart model, right? You got a big lead acid battery, you've got a throttle pedal and probably a switch, and then you drive a motor with it. How hard can it be? I've had people tell me that. Hey, electric cars, how hard can they be? Well, we're going to take a look here. So what's actually inside an electric car? Here's a picture from the GM media. This is what's inside a Chevrolet Bolt. And this one's a couple of years old. I think this was from 2019 or so. But look at the battery pack kind of sits here down on the floor with lots of interconnects. And look under, the under hood, so to speak, and you've got lots of wires, lots of cables, lots of plumbing, right? Looks simple, right? Well, let's dig into that just a little bit. So in a modern BEV, you still sort of start from the simple part. What we're going to do here is we're going to kind of build this up. I'm going to show you what that all amounts to. So first of all, you end up with the battery, and it's a fairly large battery because you need a lot of range. You want to have enough range for the customer, so it occupies a fair amount of space. Then you need to be able to control. When you got a high voltage battery, you've got specialized relays, contactors they call them, and fuses or circuit breakers, usually fuses. Bus bars or cables. You need something big and heavy and copper to move the power. This power inverter, it's got a microprocessor in it, and it's 3-phase power, and it's kind of the brains that drives this motor and makes that motor generate power in that nice torque curve. I'll just add in the contactors and so forth. There's typically what they call a battery disconnect, your service disconnect. If you were going to work on the pack, usually there's some kind of a manual switch in there to disconnect the pack. So if I go back to the Bolt, this is the battery pack, and this looks like, up on top here, looks like the manual disconnect. And you can see the orange cables. Typically orange in a car denotes the high voltage cables, and various connectors and so forth, but these are all the cells, all across here. And there's some control modules. So that's what a battery pack looks like. So if you had the golf car model with 3 or 4 lead acid batteries, this is what you get instead. Then the golf car model would say, hey, I just need a motor hooked to the wheels. And in a golf cart, right, they generally hook to a differential and an axle, but it's just the motor plugged in and kind of direct drive. Well, in a BEV, we use what we call a drive unit. And a drive unit is a transmission usually single speed. There are a few times where somebody will do a 2-speed. But usually the way the torque curve of the motor is, you don't need more than that. There's not an advantage to it. So in here you'll have the motor, you'll have the park system, you'll have the differential, you've got speed sensors, pumps, you know, it's oil lubricated. So it's a more complex piece, but a lot simpler than a 10-speed automatic, right? Then we've got charging. You know, you've got a system, you can take power out of it and drive the car, but now you got to put it back, right? And yes, I know there's regenerative braking when you're going downhill or something, but you know, that helps you a little, but eventually you get home and you got to fill up the rest of the battery. So we talk about chargers. One of the things that most people don't recognize right away is that we talked about, in fact I even talked about a little earlier, having a charger at your house. Well, the charger on the wall is actually what you might call supply equipment. It's a lot of people call it a charger, and I think they're advertised as chargers, but they just take the power from the wall and feed it to the car, and then, okay, I'm at home, right? I've got 50 amps at 220, and I got a 600 volt battery in my car. Well, you need something that converts that 220, or if you went to a DC fast charger, you have to have something that converts the voltage into something the battery can use and control that. And so you'll have a charger with solid state components in it that are, you know, modifying the current and the voltage and converting it from AC to DC and feeding it to the battery at the proper rate. So you've got a charge port, you got a charger, and then you need something here called a battery control module. And different people have different names for it, but typically in a big lithium pack, the control module has wires down to almost every cell, and it will monitor the voltages in the cells and will monitor the temperatures in the cells in a lot of cases. And it's monitoring and feeding back to the charger what the state of the battery is, so the charger knows when you're done and how much power to feed. Then you still have headlights, taillights, lights on the dash, and you don't want to run those off 600 volts. Those would be, that would be a hazard, right? So most of the cars still run on a 12 volt system. They have a 12 volt battery, and then you need something that substitutes for the alternator. And they call that an APM normally, accessory power module, that'll charge that 12 volt battery. Then you need to have some controls, right? You still need, I'm going to call the gasoline engine equivalent of an engine control module of an ECM, and in a lot of cases on a BEV we used an ECM, even though there wasn't an engine, we still called it an ECM, and used that control module and reprogrammed it to run the electric vehicle, because you still have things you need to control in the propulsion system: throttle, shift, start and stop, diagnostics for the whole system, and so forth. So there's less control than you need in a gasoline engine with variable cam timing and all of the other things there, but you need a computer, and then you need throttle control, you need shift control, and then since everything's electric, now you need electric power steering, electric power brakes. There are different ways you could get electric power brakes, but there's no engine vacuum because you don't have an engine, so you need some other way to power your assist for your brakes. There's just no vacuum. And for steering, there's no power steering pump. Now I know a lot of the newer vehicles, gas engine vehicles, have electric power steering as well. And they'll run off the alternator and the 12 volt system in most cases. But you got to have it that way on an electric car. You don't have a choice. Unless you like not having power assist. I've got cars that don't have power assist, but In today's world, most people won't tolerate that, and your customers don't like it. Next, you need to deal with thermal, right? So you have to be able to manage battery temperature. If the battery starts getting hot, you'd like to cool it. If the battery's too cold, you want a heater, you might want to heat it. And sometimes that's done with air, sometimes that's done with coolant, with liquid coolant. Basically, if you get, it depends on the cell and the cell chemistry. I mean, some chemistries, you know, when you get down around 0C or 0F, you know, they're pretty cold and they won't do much. I worked with some on hybrid where I could take my batteries down to -30 or so Fahrenheit. But at -30 Fahrenheit, the batteries I used would freeze. I mean, the electrolyte would go solid. And at that point, you can't put any current in or out until you warm them up. So in many cases, the BEVs will have supplemental heaters. Off here to the front, generally they aren't as big, but you'll often have a pump and a heat exchanger. The motors produce a lot of heat, especially at low speed. When I showed you that torque curve, it makes a lot of torque at 0 speed. Well, it's not real efficient there, and you know, it may, down at those those high torque settings, it might only be, I'm going to pick a number, 50% efficient. You could have half your electric power is going off to heat and it needs to go somewhere. So you need to cool it. The drive units I've been associated with will typically have oil cooling. Splash oil, the motors will have oil in some form. And you'll need a pump to circulate the lube oil. You'll have a heat exchanger off to the front to reject that heat. It won't be anything the size of a gas engine radiator, but you do need some heat exchangers somewhere. Then we'll go last, right? Now the passengers would like to be comfortable. And so if you want heat in the car, a gas engine, you've got coolant, you know, right there, your coolant is hot, and so you've got a natural way to heat the car. Now you need an electric heating element, and you need, for cooling, you need an electric AC compressor, an electric air conditioning compressor, because you don't have an accessory drive belt on the engine to drive one anymore. And so the interesting thing when you get all through this, I had an engineer I was working with who was responsible for the propulsion related components and modules for a Bolt, Chevy Bolt. And this isn't all the modules in the car, but he was responsible for more than 20, I think it was 21 modules, control modules and elements to make the powertrain system go, the propulsion system go. If you've got an electric AC motor, you need some kind of module to drive it and command it, and then you need the motor. If you got an electric heater, you got to have something to control the electric heater. That's the complexity. Now, many of these things are durable for a long time, and there's no maintenance to speak of on them. They're pretty solid. But the complexity is a lot higher than the golf cart model would suggest. Now, technology. Why, in the last 20 years or so, can we build electric cars and hybrid cars, and we couldn't before? What happened? What's different? Well, the answer to that is microprocessors. The computer control technology has gotten so sophisticated that, as laptop or desktop computers, through the 80s and 90s got more and more powerful, and microelectronics got smaller and smaller. There are certain things you need to do to make these systems work well. And so the first one is you have power inverters that generate three-phase AC power from a DC source, and you have to take DC power and convert it into, you can see here in the picture, three-phase. So there's one-phase, two-phase, three-phase. Three-phase AC is very, very effective at driving motors. Now, typically in an industrial setting, people have three-phase motors, but they're 60 cycles, 60 hertz, standard power in the United States. In Europe, I think it's 50, but in the United States, it's 60 cycles. And so three-phase power at 60 cycle will drive a motor, but it'll drive that motor at a constant speed. It won't drive it at a variable speed unless you do something really fancy. So three-phase power inverter with microprocessor control, you're not stuck at 60 hertz. You can run it at 30 hertz, you can run it at 100 hertz, you can run it at 1,000 hertz, and you can change the frequency and you can change the amplitude by how you control the solid state parts inside that inverter. I'm oversimplifying it, but from a car enthusiast's point of view, that's kind of the magic knob number one. Magic knob number two was lithium-ion batteries. When I started on hybrids, my first hybrid started with a lead-acid battery. The life on that wasn't really good. We were working it pretty hard, and it wasn't going to probably last the life of the car. We ended up on the first one going to a nickel metal hydride battery, which actually had excellent life. But then when lithium came, lithium is even lighter than a nickel battery. It has more energy storage, and that's really become the enabler for a BEV. The third one is in the motor guys. Not everybody does it, but traditionally, these pictured down on the right with round wire, typically we always wound motors with wire. You make your stator winding with stranded wire, single strands, and you wind them through, and you make a winding, and you make circuits, so that's a three-phase capable. Now the technology has gotten into rectangular wire, or what a lot of people call bar wound. But if you figure that, round wire, it's a circle, right? If you want to get more energy through the same thing, you need more cross-sectional area. So now you cut wire in rectangles instead of making it round. And the challenge with that is that you have to be able to weld the pieces together. You can't just wind them. To make a winding, you can take a look at this one that says bar wound. You have to have machines that can bend this, put in straight pieces of wire, bend them to a shape, and then weld the connections at the end. And there are probably more enablers, but those are the three big ones that I saw from my time in the business, I'll call it. Now, if you're a horsepower enthusiast and you want to make more power, what can you do? Is there anything you can do? And the answer is probably not a lot. These systems are very tightly integrated, and the performance is controlled by your battery voltage and your cell design. And when I say cell design, it's the chemistry and it's the internal, how the electrodes are laid out and how the cell is constructed. And battery manufacturing and design, that's a very specific topic, and there's continuing development. Every year they come up with a better one. Sizes of the cables on the bus bars. Sometimes the cables that go from the battery over to the motor or over to the inverter, sometimes they could be larger, and you'd have less loss. But packaging them in the car is often very difficult, and it's also very expensive, and so it depends. That's one of the limiting factors. The basic motor windings and the basic design of the motor, unless you're going to find somebody who can design you a brand new motor, there's no dropping in a cam or hooking headers on it, right? It's kind of a different animal. You almost have to take the whole motor unit out, and then when it's integrated in a drive unit, perhaps someday will come where we'll get some folks in I'll call it in the racing world, who come up with special windings that you can plug in that change the power and the torque curve of your car. but it won't be something that you can do in your backyard. Motor control tuning, motor control computer tuning. In my experience, we had calibration engineers working in the lab, and they would take our motor designs and they would take our inverters and they would run them on the bench, against the dynamometer, and they would spend weeks, months tuning that motor's performance all the way across the speed range to get the best that they could get out of it. Generally, we wanted to map the motor so we got peak power no matter what, and we also wanted to get peak efficiency. And we would want peak power and we would want peak efficiency, based on a specific map. And we didn't usually leave much on the table. I mean, motor engineers really went a long ways in calibrating the motor control. And the little picture at the bottom, that's kind of the schematic, roughly. You got a battery. You got a pair of cables, that run over to the power inverter. It converts it to three-phase AC and sends it to the drive unit. Now, I'll go on a short tangent. Three-phase isn't the limit. There are people working on more phases. You could run a six-phase motor if you wanted to. Out in the advanced world, there are people working on other motor designs that would have different arrangements. But everything I worked on, we used three-phase. We talked about going further, but that was kind of where we were at. So summary, bottom line, the electric cars are all around us. There are more on the way. They've got good performance. They're quiet. The maintenance is better. But they're more complex than most people would catch, at a glance. But properly designed and operated, they can run as long as a conventional car if you get a good design. Some people are going to have trouble. I'll say I'm going to say I'm one of them, right? I have trailers I like to tow, and I like to drive long distance. I make trips to see family long distances away. And I'm not ready to make half-hour stops every couple of 100 miles to bring my battery back up. It's just, my lifestyle is that, I go drive as far as I can, and then I make a 10-minute stop to put gas in it, and then I keep on going. And I'm not ready to trade that yet, and frankly, with the size of some of the trailers I pull, I don't know that I can get there from here yet. Now, the day may come. I'm not slamming the door on them, but those will be. If I was running city full time, short distances, electric car would probably be just fine. And charge at home would be just fine. So it just depends on the customer and how you want to go. And then finally, the performance upgrades. Those of us who like classic cars, and hey, we may have some really good classic electric cars in 20 years. We all want to keep on going with. They're just going to be a whole different character than what we're used to. So I hope that was enlightening. Hopefully I didn't bore you by the amount of time I took on this, but that's how life is right now with electric cars, and this is what's coming toward us in the I was going to say years to come, but it's in the months to come, right? All the car companies are working to bring this stuff to market, and every one of us is going to be encountering it, and that's all for now.